Anyone else? Oh.
Hey. So, you know me already. My name is Steffen Rupp. I am from the Fraunhofer Institute for Surface Technology and Biotechnology. I showed you our work on biosurfactants. We are thinking of continuing this work, but also in another direction, more into cosmetic or maybe food applications for different MALs and so on. If you would be a company that is involved in this factor, in this area, or have experience in the cosmetics, food application industries, you would be very welcome to join here this proposal. What I can offer also to other consortia is that we do have a wide application range in molecular biotechnology, so we are able to modify different types of strains, from Cerevisiae to different type of fungi. We have also process engineering facilities from multi-fermentation units, 1 liter up to 40 liters of fermentation capacity. It could go up with the partner institutes also to 1 cubic meter, 10 cubic meter scale. What we also do is next generation sequencing. So we could go into pathway analysis, as I've shown you briefly, and combine this also with proteomics with a multi-TOF that we can use for pathway analysis. And typical classical chemical analytics is also available. So very brief, short roundup. If you're interested, just contact me. Thank you very much.
Okay, must be someone local who wants to sort of say how fantastic the research is in Warsaw. Surely somebody wants to tell us how fantastic things are here in Poland. Must be someone. No? I can't make anyone feel guilty. Okay. Harvard, do you want to say anything about Syntef? Go on, you know you want to. See, if I know somebody, I can put pressure on them, can't I?
Hello. So my name is Håvard Sletta. I'm from Norway, from Syntef. I don't know if you know Syntef. We are a research foundation, much like VTT and Fraunhofer. And, we are in Scandinavia, and approximately 2,000 people. On the biotech side, which I represent, we are currently involved in 2 projects financed by this ERA IB call, but we want to be a partner in more projects, and maybe we try to host a project for this call. I don't know yet. That's why I'm here. I'm looking for partners and see what's going on. It's a lot of really good presentations that we have heard today, so it's a very interesting meeting. So what we can offer, we have more or less everything from molecular biology. We have a large screening facility, been working with industry and strain and process development for many, many years. And we also have a fermentation facility with more than 40 fermenters from 1 liter up to 300 liter pilot plant. And we also have a large analytical facility with more than 20 MS instruments running, doing all sorts of analysis, also on very much on high throughput assays. So that was a short presentation. It's okay.
Thank you. Okay, is anyone else? Must be somebody. No? Really? This is your chance to say how wonderful you are. Okay, Karen, what do you think? Can someone check to see if we can break for lunch now? Otherwise, we're going to have to. I don't want to send you all down for lunch and then get very upset if it's not ready. We might have to do one more talk. Is the MicroTechEnz person here? Oh, you're here. What do you think? I think we should do one more talk. Yeah, let's do one more talk, as that didn't fill up enough time. You're all too shy. That's okay. I know what it's like to be shy. We're going to do one more talk then. Where's your talk?
Final meeting, the last.
This one? Okay.
So this is to go. What is to go? This is.
Yeah.
This is to go.
Yeah.
Okay. Okay. Good morning to everyone. My name is Đurđa Vasić-Rački. I was coordinator of the project Microreactor Technology for Continuous Enzymatic Reaction Catalyzed by CC Bond-Forming Enzymes. In the project, we have 4 partners. One was the University of Zagreb, Faculty of Chemical Engineering and Technology, and the group leader in Zagreb was Associate Professor Zvijezdana Findrik-Blažević. Partner 2 was Institute of Bio and Geosciences from the Department Biotechnology from Forschungszentrum Jülich in Germany, and the group leader there was Professor Martina Pohl. The partner 3 was the Institute of Advanced Chemistry of Catalonia, and the group leader there was Professor Pere Claps. And in our project, we have the one BioGlane. This is a small SME with the Mr. Sergi Pumarola as the group leader there. The main goal of the project was the evaluation of the microreactor technology as an appropriate tool for the rapid screening of the enzyme activity and parameter optimization for biotechnological production of important compounds. To achieve this goal, we put some topics in our work. The first selection of thiamin, diphosphate-dependent carboligase, and D-fructose 6-phosphate aldolase for the studied biotransformations. Then we wanted to compare a microreactor technology with classical types of reactors in the reaction catalyzed by DHAP-dependent carboligase and FSA. Establishment of microreactor concept using magnetic beads to immobilize benzoyl formate decarboxylase with the terminal hexahistidine residue. Preparation and characterization of 3 FSA variants, and the development and implementation, the cascade reactions to produce valuable compounds in microreactors. The first enzyme we selected was benzoyl formiate decarboxylase. This is THDP-dependent enzyme from Pseudomonas putida. With this benzyme, we synthesize chiral S2-hydroxypropiophenone from benzaldehyde and acetaldehyde. And this chiral product is also the precursor in the enzymatic synthesis of chiral alcohol and any other valuable compounds. This synthesis we performed in batch reactor, in repetitive batch reactor, and also in continuously operated ultrafiltration membrane reactor. We used here a small laboratory reactor. This is a flat ultrafiltration membrane reactor, where the ultrafiltration membrane reactor retained all the enzyme in reaction vessels, while the substrate is flowing through the reactor, and the enforced flow through the reactor ensure that we have some convective transport through the membrane reactor, and that we did not have any diffusion resistance, and therefore this reactor was working as continuously starched tank reactor. Then we used micro-reactors, and we used two strategies in microreactors. We used the soluble enzyme and also the immobilized enzyme. And with soluble enzyme, we used simple fluidic flow reactors, and also the concept where we try to recirculating our enzyme in the system, and on this way also retained the enzyme longer in our system. First of all, I will present you some results what we get with this soluble enzyme in this classical fluidic flow microreactor. We use three types of these microreactors. The microreactors with with the rough surface on microreactors chip walls, and also the smooth microreactors chip walls. And the third kind of this microreactor was microreactors with teardrops mixer structure, and at very low residence time for this synthesis, we got the next results of higher volume productivity, which was 7 to 70-fold higher than in ultrafiltration membrane reactor, and also 3 to 5-fold higher volume productivity when we compared this productivity with a batch reactor. So also the higher volume productivity we got in this microreactor with this special structure of micro-mixing. The data about this research was already published. Then we used this reactor combining with the recirculation of the water phase. Here we were using this separation from organic phase and this water phase, and on that way we tried to retain some enzyme longer time in the reactor. What we saw from this approach, that the enzyme can be a little bit prolongated use than in our ultrafiltration membrane reactor, which was worked also continuously. But in that reactor, in this mixer, in this reaction vessel, we have some mechanical mixer, and because of that, maybe the enzyme deactivation was faster than in our microreactor device. Let me here to summarize these results. When we compared these types of classical reactor we used with our microreactors, what we use, we saw that really we had and we got the best. Sorry. Oh, sorry. We got the better volume productivity here in microreactor with enzyme recirculation pump. Also, biocatalyst productivity number, the number which told us how many enzymes we need per some special amount of enzyme. This number told us that almost in all of our reactors, except of this reactor, which is repetitive batch, we could run this reactor 4 times in 4 cycle times, and therefore this number is almost the same in all types of reactor. So, beside this flow reactor, I told you at the beginning, we immobilized enzyme on magnetic beads and constructed a new parallelized microfluidic reactor. This microfluidic beads was put in the microfluidic channel, and in this microfluidic channel, these beads was mixed and also retained in microfluidic channel by means of permanent magnet in these wheels, which was, this wheels was rotating and was put next to the chip. The whole setup of this reactor has 3 chips, as you see here, and about this reactor, the 2 patent application was already filled. And if somebody of you are interested more in this kind of reactor, Professor Martina Paul is here, and she can give you some more detail about this kind of completely new microreactor. So now I would like to present the result, what we got with this D-fructose 6-phosphate aldolase. This aldolase was specific because took this dihydroxyacetone. This is not phosphorylized, and on that way we can produce some aldol, which is a precursor of D-fagomine, one amino sugars, which is very useful and has some special biotechnological properties. Partner from Barcelona prepared 38 different variants of these enzymes, and 3 of these variants were sent to partner 1 in Zagreb, and partner 1 in Zagreb then characterized kinetically this enzyme, and also performed this reaction in batch reactor, in continuously operated ultrafiltration membrane reactor, and also in microreactor. In this classical microreactor with this fluidic flow, this is commercial microreactor for Micronit.